Okay, hello everyone. This is another video partially involving supersonic flow, but also partially involving just something I wanted to mess around with a little bit, so I might as well talk about it a little bit while I'm doing it. So I'm going to attempt to model not any one in particular, but just kind of a generic, arbitrary convergent divergent nozzle. And use a couple of features that we haven't really talked about. So, as soon as this loads up, we will start with this. But we're going to use a couple tools that we're not familiar with. And I'm going to try and use a much more advanced thing, which is the fact that the exhaust from this nozzle is not going to be air. It's going to be something else. This is a multi-species flow. Or I'm going to try and get it to work. I might not be able to succeed. We'll see. But clearly it's going to be very difficult to define a convergent divergent nozzle with basic spheres and other things like that. So we're going to actually make a new 3D CAD model. This is simultaneously a fairly basic tool, but also potentially quite powerful, as it has pretty much all the functions you'd expect in a normal CAD tool without some of the graphical niceties that you might normally expect to have. So we're going to start with our combustion chamber inlet here, where this is horizontal, I believe. Yep, that's what that constraint means. So yep, it's set as a horizontal constraint. So I'm going to do a couple things here. I'm going to create a couple of construction lines. So these lines I want to be construction. I'm going to set this one a dimension. This is going to be the radius of our chamber. So we're going to go with 2 inches. This one is going to have a length of 8 inches. So this is going to be our kind of combustion chamber run-up. This is probably... Actually, no, I'm going to make this 6 inches. This is completely arbitrary. No science behind this whatsoever. I'm going to make these equal length, and I'm going to attempt to anchor this. 0, 0. So we're going to fix this one point at the origin so it doesn't move around. So at this point, I think this should be fully defined. None of this should go anywhere. So now we need to start with a convergent divergent section. So we're going to do a area ratio. We're going to reduce the area by a factor of 9 into this throat. So we're going to start with a pretty arbitrary center point. Okay, let me try this some other way. Here, there. Okay. So we're going to make these 2 lines tangent starters. We're going to also merge these 2 points. So I'm doing a whole lot of right-clicking to set this. So we have our curve that begins the convergent section. Let's do something like yay and that. These are not actually fixed to be tangent, so we're going to tell them that these are tangent. Perfect. So if I create a line that is on this curve and horizontal, I'm going to make this a construction line, set as construction. I'm going to make this tangent to this line. And I'm going to bring this line over here so it's coincident. So this kind of adjusts that. So if I set a distance constraint, let's see, can I actually do this? Hold up. I want to see if I can make this a function. Actually, hold on. I'm going to expose this. I'm going to make this. So expose this parameter means I can modify it. Modify it from outside of the 3D CAD environment inside of Star. We're going to apply a distance. We're going to make this equal to let me see here. I believe the way we define a parameter is $, open curly bracket, close curly bracket. Yep. Doesn't seem to like that. $, close, chamber, radius. I didn't like that. Let's see. Divided by 3 inches. Okay, whatever. 0.667 inches. We're going to do this the hard way. So that radius difference is a factor of 3, which means the area ratio should be a factor of 9. So these we're going to make equal radius. And the only other thing is we're going to do this. Oh, right, okay. Right, because it specifically goes that way. We're going to make these endpoints coincident. We're going to make these endpoints tangent. And we want to draw a line that is going to be start there and be horizontal. We want this endpoint to end over here, so set coincident. We're going to make this construction line. We're going to make this construction line tangent to this. Means this nozzle is going to end up. Being it is going to end up being a horizontal departure at the end. Now the only issue here is while this is absolutely tangent, I probably don't want these to have equal radius. Go ahead and delete that. So this distance, we reduced our area by a factor of 9. Let's increase it also by a factor of 9. So this is going to go out to a 6-inch radius all told, but we need to do it over a relatively long distance. Not quite that, or I mean, the issue is in part. Let's see here. That's tangent, that's fine. Okay. I think part of this is I need to start to dimension some of these radiuses to keep them from getting too crazy. So we're going to make this radius, let's say, 0.1. Try that. Okay, better. And we're also going to make it so this point does not actually need to be. This can, and probably should, be very far down off there. There we go. That looks so much better. Okay, so we're going to go ahead and, without any particular attention to how physically plausible this is, we're going to attempt to make a wall thickness for this, which we're then going, there we go, which we're going to basically cut through our, or we're going to revolve this, and that will be our actual engine bell slash combustion chamber walls. So they're going to be, 0.1, that's a centimeter. So that's like, you can do the math, 2.5 centimeters to an inch. So we can do let's do just a quarter inch. 0.25 inches. Cap extensions, bevel edges. Let me get rid of this. And let's try that again. Offset primitive. Bevel the edges. Okay. It didn't do anything for the end caps here, so I'm going to just do it for that. This is probably okay. Did I actually define a distance here? Oh, yes, I did. 6 inches. Okay. Okay. So this is our engine bell. Click OK. This should be a closed shape, I think. Let's try and revolve this. But not about that axis. That would be bad. Direction, normal. I'm going to specify the axis. I want to revolve it around the x-axis. And I would like to revolve it by 360 degrees. And I'd also like it to merge into one block and all the other good stuff. So, merge, if it encountered another body, it would merge into it. It's a solid body. It's normal to the plane. Or as opposed to reverse. Doesn't really matter for this case. I could do a two-way symmetric, two-way asymmetric revolve. Doesn't really matter. That should be fine. Go ahead and click OK. Hey, we have a rocket nozzle. Okay, perfect. So now we can take this and we can make it into a geometry part. We want it to hold the 3D CAD association, so if we modify the CAD, it will modify our part. All CAD edges, that's probably fine. Okay. We have a body, but we have no geometry scene. So let's create a new geometry scene. There's our rocket nozzle. Not sure how good it's going to be. Entirely arbitrary, but we'll give it a go. So, what I'm going to try and do, for the sake of simplicity and making this run fast enough, is we're going to try and do a two-dimensional axisymmetric simulation. So, how is this going to work? Well, we're going to create a block. As before, one corner of this is going to exist at z equals 0. I'm going to have this start 6 inches upstream. -6 inches. Theoretically, that should be exactly parallel with that face right there. And actually, I'm going to have it start ever so slightly in from that, just so we make sure that this is clipping out of the block ever so slightly. This is going to go something relatively silly, like 30 meters downstream. And that's probably going to be too far. We don't need to go that far. Honestly, we probably don't even need that. We'll do 1.5 meters. That's probably... we'll do 2.5 meters, because I don't know if this is over, under expanded, or any of the other good stuff. And we'll do 1 meter. It's kind of for the hell of it. Or we'll make it a square thing, 2.5 meters. So if we want to do a quarter of an engine bell, we could, 3-dimensionally. We're going to try and do this 2-dimensionally, though. So now we're just kind of doing exactly what we did before. We're going to do a subtract. We're going to subtract our body from our block. We have a subtract. However, we did not split the surface of our block. Let's split by angle so we get all 6 surfaces. And let's run this subtract again. Execute. Okay. Inherited parts. Well, this actually could be a little bit awkward. Because we want these to have different inlet conditions, right? So, is there any way we can split that? Not really. Not easily. I'm trying to think of a good way to do this. Okay. Here's what we're going to do. We're actually not going to start the block here. We're going to start the block at 0. And this will make sense in a second here. So our block starts there. Now, this is a problem because we definitely need to run up to this constriction. We need some distance up here. So we're going to create a cylinder. New part, new shape part, cylinder. It's going to start -6 inches and proceed to 0. We're going to have a diameter of, a radius, excuse me, of 2 inches. This theoretical, and actually I'm going to make this slightly oversized on the radius. So we're going to do 2.1. And we're actually going to have it continue a little bit upstream. So if we have it, continue 1 inch upstream. Okay, we're going to create that. This cylinder, that's fine. We're going to split by angle, so we should have an end, 2 ends, and a sidewall. And we're going to subtract, Boolean subtract, our body, that is our rocket engine, from our cylinder. This gives us a second subtract. And now, here's what we can do, I think. Inherited parts, our cylinder. Yes, we have... Oh. Okay. I need to do another Boolean here. So we're going to create another block. Because the problem is the main block is a quarter, so we need the cylinder to be a quarter of a cylinder. Inconvenient, but so it goes. So -6 inches, 0, 0, 0.5, 2.5, and like 15 again. Okay, create. So what I'm going to do here is I'm going to do a Boolean unite, or not Boolean unite. Intersect. That's the word I'm looking for. So we're going to intersect our subtract and our block. So this is going to create a volume where they intersect and only where they intersect. We now have a quarter of a cylinder that has the interior of that engine and doesn't have anything that is part of the walls. Okay, now we can do a Boolean unite of our intersect and our first subtract. There we go. That's what we're after. And importantly, we have the ability to define multiple. We should have the ability to define multiple boundary conditions. Oh, except not quite. I need to split my second block. But other than that, we should be okay. Split by angle. Click OK. Rerun all of these. Execute all. Inherited parts. Block. Subtract. The cylinder. Aha! There we go. That's what we needed. That's one of our. That's our inlet for that. Oh, this is the unite, not the. Wait, no, this is. Yeah, no, that is the unite. That's what I wanted. One of our blocks. Ah, here we go. Here's the other block. Perfect. Okay. So, this should be exactly what we need. So, I'm going to try, see if this works, to badge our unite for 2D meshing. Let's go take our unite. Oh, it properly badged it. Look at that. Wait, what the hell did I just right-click? Right-click. Oh, I said select mesh operation. That's not what I wanted. I want to create a region. So we're assigning it to a region. Apply. There should be a region for it. Now let's try and mesh it. New mesh operation, automated mesh 2D. We're going to do a poly mesh with prism layers on our unite. The only reason our unite showed up was because we just badged it for 2D meshing. So base size, we're going to do... I'm going to go with 0.5 centimeter. We're going to need to create a whole bunch of surface controls here, probably. So on this unite, on the subtract, on the block, these are going to be our far field controls. I am going to create a cone or a cylinder we can use to sort of refine. You know what? I am going to make it a cone. 0, 0. So we're going to go, let's do like 10 meters downstream. It's going to start with a radius of like 0.25. Yeah, that's probably pretty good. There we go. So we're going to have a volume refine on this cone here. So this is our far field refine. We don't particularly want it to be a very coarse mesh or very fine mesh here. And we also want to disable prism layers. Prism layers disabled. We're going to crank this up to something like 1600%. And minimum base size is going to be 100. We're going to create a new surface control. for the entire surface, which is going to say, hey, you have a max size, custom, you have a max size of 1600. It's never going to get any bigger than that. Okay. Max size. We're going to create a new volumetric control, which is going to encompass our cone. And this is going to say, hey, make sure this doesn't get above 200% base size. I'm going to let the minimum get real small as needed. We're going to probably want more prism layers. We'll do 8. I have no idea if this is going to be good enough or not. We'll find out. And 50% prism layer thickness. We also want to do probably a refinement on our inlet because it's going to be a relatively high pressure. So I'm going to create actually a cylinder here. It's going to go from -6 inches to +2 inches. Actually, let's do like +12 inches. 24. So I basically wanted to capture all of the flow inside of the nozzle. We want this to be a very, very small refinement. So this is going to be... Actually, I probably need this to be a cone now that I think about it. New shape part, cone. We're going to start it at -6 inches. It's going to go to 24 inches. Nothing in the Z direction. It's going to go to a diameter of 6 inches. I believe that's how big I made the outlet. Yeah, look at that. Okay, maybe slightly larger than that. We'll do 6.5. And we're going to start this at a diameter of 2.125 inches. So theoretically, this... Yeah, that cuts it a little bit close, but theoretically, this entirely encapsulates the flow inside of that nozzle. So, volumetric control, we already did that one. We're going to create a new volumetric control. This is for the flow entirely inside of the nozzle. So this is cone 2. Surface control. This is going to be even smaller. Save rocket. Oh, access. Oh, yep, because by default it tries to save in that frickin' directory. Let's go back out to the share. This. What time is it anyways? 10:30. Let's see how overzealous I was, if I was at all. Scenes. Let's create a new mesh scene and see what this looks like. Oh dear. Yeah, actually, I could probably go a bit finer than that. We're actually going to knock the base size down to 0.25 centimeters. Going to make this first volumetric control 100. I'm going to try that again. I might have overcooked it a little bit with that. Let's do 0.375. And we'll make that volumetric control, we'll split the difference. We'll go 150%. Cute. Oh, do you see an issue here? Yep. So that needs some help right there. I messed that up a little bit. So we need to add a couple of things. There we go. That should be fine, I think, because we're also making the cells relatively small in that region. To the point that I might even make them a little bit smaller. I'm going to kick this out to like 7.25, 7.5. Let's start this at like 2.5. I just want to catch the outside of this nozzle because there's going to be flow interacting with it. This is going to be an inlet over here on the left. I do rather like most of how this is turning out as it is. But things are about to get interesting once we apply physics to this. Okay. That's more or less what I want, yeah. Okay. Okay. Pretty good. I like how most of this looks. I might need to turn down the max size a little bit, but we'll put a pin in that for now. For now, let's select physics. Physics. Okay. This is going to be steady flow. It's going to be a multi-component gas simulation. There's going to be more than one gas. Coupled flow, ideal gas. It is going to be turbulent. We're going to use K omega. That ought to be it. Okay. So, how do we deal with multi-component gases? Well, you define your components. So, under models, multi-component gas, we can select our gas components and select our components from a handy material database of gases. We're going to select air as one of them. And we are going to select carbon dioxide as the other one. Carbon dioxide and water, actually. Now, I'm not exactly sure. Let me actually come up here and okay. So, oh, that's nice. We're gonna do stoichiometric combustion of methane. Not entirely out of nowhere because methane makes a perfectly fine rocket fuel. But we need to make sure that we're, actually burning something. So, what boundaries do we have? This is going to be an inlet. This is going to be a stagnation inlet, specifically. Stagnation inlet. This is where we're assuming completely combusted methane is entering. Stoichiometrically combusted methane with oxygen. Species specification is going to be a molar fraction because doing the stoichiometry is easy in a molar sense, more difficult in a mass sense. Flow is coming in, boundary normal is fine. The species mole fraction. Well, how do we specify what species we have? We need to note very precisely the order. We have air, water, carbon dioxide. So the stoichiometric combustion of methane should yield 1 mole of carbon dioxide for 2 moles of water. So 0 space 1 space 2, I think. Did I get that right? Nope. 0 space 2 space 1. So 0 air, 2 water, 1 carbon dioxide. The supersonic static pressure, I have no idea what's reasonable. Let's do 20 bar. Total pressure will be 20.5 bar. It's coming in with some velocity. 1200 Kelvin. Shrug. Just kind of making numbers up for that one. Definitely do not assume that I know what I'm doing with that. I'm just messing around with different things here. Oh, I messed up, didn't I? Select models. I selected two-dimensional, axisymmetric. There's a very big difference. We're not simulating a linear rocket engine. We're simulating a circular rocket engine. I literally just changed it to axis. That shouldn't be a problem. Okay. Small tweak, I guess. Oh no, that should be fine. Why was it complaining? Axis. So if I change it to anything else, it complains. That's fine. Because we're setting it to an axis. That's fine. This is going to be a free stream inlet. Flow direction is positive x. Mach number 0.7. Sure, why not? Species mass fraction. This one is all air. This is air coming in through this left out inlet. This is going to be a pressure outlet. Now, we still do need to specify a mass fraction on our pressure outlet, just because if there's backflow, it needs to know what's coming back. That's fine. It's going to be air. And this we're going to make also a pressure outlet. Same deal. We're going to tell it that if there is any backflow through the surface, it's going to be air. Now these other boundaries should just be walls. So let's just make sure here. Yeah, those are just walls. That's fine. They're adiabatic walls, which isn't really all that realistic, but we're going to run with it. We're going to make sure our axis is the x-axis for this region. There's no energy source option, no species source option, no turbulent source. We're going to see if this works. I wouldn't hold my breath. If it was an actual rocket engine, I would hold my breath around it. Sum of mass or mole fractions, 0 on ignite. Pardon? Did I not set one of these somehow? Oh, initial conditions. Right. Also, I need to probably read this. Initial conditions. Ah, yes. The initial species mass fraction will be 1 space 0 space 0. So it's going to start as all air, and it's going to basically purge and start. Attempt to purge and start. We'll see how well it works. Reference values, reference pressures, 101.5, that's fine. Save, initialize, rug. It's doing stuff. Okay, let's see here. Scenes, new scene, scalar. Let's take a look at static pressure. There we go. Okay. So we're also going to open up a new vector scene. This is going to plot velocity, but it's going to plot it with a line integral convolution. Uh-oh, it didn't like that very much. Okay, where are my solver settings? Automatic CFL. I'm gonna let it go even lower if it thinks it needs to. Also gonna plot Mach number. Because these values were chosen completely at random and may or may not represent a realistic case. Matter of fact, they probably don't represent a realistic case, if we're honest. Yeah, okay, tell you what. We're gonna change this up just a little bit. We're going to bump down our chamber pressure. We might be able to elevate it later, but for the moment, we're going to lower this. That's probably another good thing. Minimum allowable pressure will do 10 pascals. Minimum allowable temperature, we're going to do 10 Kelvin. Even though it's probably lower than it needs, that's fine. Wall distance, fine. Pressure, not really going to be increased, I don't think. But it's definitely wanting to diverge. Look at that Mach number, it's just blowing up. Stop. That's not good. Let's see here. So, I take a look at this. Let's just do 10 bar exactly. Total temperature 1200 Kelvin. So theoretically, this should be coming in with a velocity of damn near 0. Will accelerate because there's a large pressure difference driving it. That's definitely curious. Why is it doing that? Oh. 240 space 0. Your solution. Yeah, that looks like it's just diverging. Okay, so what we're going to do, actually, we're going to slowly... Actually, we're going to see what other kind of boundary conditions we have. If we just do a velocity inlet, what do we specify? Not enough. If we specify... We'll leave it as a stagnation inlet. But we're going to start it at 1 bar, and we're going to slowly step it up. We're actually going to make a parameter do this. That's going to get real old real fast. New parameter is going to be a scalar. It's going to be pressure. It's going to be chamber pressure. Chamber pressure. This is going to be, we're going to start it at 1 bar. And we're going to set both of these, where they go, not that one. Here we go. Both of these we're going to set to our parameter of chamber pressure. Chamber pressure. Okay. There we go. Much more sedate. So we will need to step it up, but we're starting to get more or less what we expect, which is we're getting constricted flow and then it's accelerating. Let's do 2. Okay, let me stop this for a second. Save. Let's see here. Where did I put my solver settings? Uh-oh. That doesn't look friendly. Is this actually going to start coming back down, or is it just going to sit there? I know that's pretty under. Tell you what, we're going to change our boundary condition because I don't like this stagnation inlet that's doing. We're going to change this to a free stream. A nice sedate Mach 0.05 Mach number. This pressure is going to be our chamber pressure. Okay. Okay. The species fraction is still the same. This is going to be 1200K. We're going to clear out our solution. Try this again. Oh, I typoed that, didn't I? Chamber pressure 0, 0. It couldn't evaluate that because that's not a valid equation. Okay, that's what's going on. Let's do. So what was happening is, as it was trying to accelerate, pressure was dropping so far that there was a threshold where it basically got to vacuum pressure. You can't go any lower than a true vacuum. So there was a hard stop there where it stopped accelerating, which caused a normal shock, I believe. Which is why we saw that region of very fast flow and then a region of very slow flow. Where's our Mach number? Yeah, it looks like it's still doing it though. Yeah, because it's getting low enough where. So what I'm gonna do is, for this scalar field for static pressure, what I'm gonna do is I'm gonna have it trim this field below the minimum. I'm gonna have it trim at 95,000 pascals. Yeah, look at that. Right there. So more pressure, I think. Oh, that's closer, but it's still not. Actually, hold on. Okay, screw it. We're gonna go with 200 bar because apparently I just did it quickly. The Raptor is supposed to have a chamber pressure of like 300. So we're gonna go 200 and see what we get. This is a pretty aggressive area ratio because this is an area ratio of 9. So this is an area ratio of 9 to 9, which is 81. That's a huge area ratio. I think part of this might just be mesh issue. What I'm going to do here is I'm going to refine this a little bit. Specifically, I'm also kind of interested in, not this entire thing per se, but we're going to take this cone and we're going to make another cone. Oh, did that not? Okay, whatever. Paste. Okay. So what we're going to do here is this is going to go, we're just going to make this like 40 inches. So we're going to have a cone and a cone. We're going to use both of these for our volume refine. Also going to make this volume refine finer. It's going to be a 25% refine. It's cute. And we're also going to bump our chamber pressure again. And also bump our chamber temperature. Let's see. Static temperature, like 2800. Now we just kind of wait, I guess. I'm gonna pause this. Pause this recording, that is. And just kind of let this do its thing for a while. Small addendum. What I'm trying to do here is decided to just make this pull this nozzle in. So hopefully we'll see this remesh in just a second here. Several seconds here. And we'll see the narrower nozzle outlet just to pull that area ratio in. Because it occurs to me a throat to outlet area of 81 might be a bit extreme. So we're going to pull that down some and see if that fixes our issue. Again, this is an entirely arbitrary thing. No design has gone into this rocket. None whatsoever. Well, like I said before, we'll just let this go for a little bit. Okay, this appears to be more or less doing the right thing, but it's going to take a while to get there. So I'm going to let it just keep on going for a while. And I'm going to stop this recording entirely, not just pause it. And go ahead and post it now, and we can revisit this later.